Hello everyone, welcome back to the tutorial series on microcontroller peripherals and interfacing, and today's topic is ADC interfacing with 8051. So let's begin with the topic. As we all know, nowadays all the things are becoming digital and digital, like digital phones, digital cameras, digital watch and so on. But the quest is that the real world is analog. Then how is this possible? It's all because of ADC. ADC stands for analog to digital converter. The name itself says that it converts analog signal into digital signal. What you see here is the person is speaking, and this voice signal is given to the ADC. Then ADC converts the voice signal into a digital signal, that is series of zeros and ones. Many real life quantities are available in analog form like temperature, pressure, humidity and so on. So if you want to process this signal, then you have to convert this signal into digital one. So we'll see how to do it. Next is what does an A to D converter actually do? Two main steps of process are, first one is sampling and second one is quantization and encoding. Sampling means measuring analog signal at uniform time intervals, that means taking samples of analog signal. And the rate of sampling is twice as fast as what we are sampling. Means the frequency of this signal is twice the frequency of the original analog signal. And at the output of sampling we get these waveforms, means we are taking the samples of input signal. Then this signal is given to the quantization and encoding block. Then what the quantization process does? Quantization is the process of approximation to the closest possible value. If the two input values are 0.3 and 0.35 and these are closer to each other, then we will consider it as 0.35 only. Means we are approximating the two signals. Then encoding means assigning a digital value 0 or 1 to the analog signals. This is the simple process of A to D conversion. There are so many techniques for analog to digital conversion. We will see it later on. Then when we think of ADC, then what we think is the important characteristics of ADC. So let's begin the characteristics of ADC. But before this, what does it mean for us? Why do we think of this? Is it really important for us? Then we'll see first the resolution. Resolution means number of output bits. If the 8 output bits are there, then the resolution of that ADC is 8 bit. Let the maximum output of a sensor is 5 volt, and if we give a 0 volt input, then we will get a 0 0 0 at the output, and if we give a 5 volt input, then we will get a 1 1 1 at the output. And if the input voltage is in between 0 to 5 volt, then the output levels are also in between 0 0 0 to 1 1 1. But when the state changes from 0 0 0 to 0 0 1, at what instant the state changes? To calculate this, we have to know the electrical input voltage for 001 level. I have calculated the electrical input voltage for 001 level. It comes out to be 74 millivolt. You might be thinking then how it comes. Then do simple cross multiplication of these two things. You will get the 714 millivolt approximately. But what this indicates? This means that below 714 millivolt there is no change in output state until and unless the input voltage goes beyond the 714 millivolt. There is no change in the output. Means after every 714 millivolt there is a change in output state. Next is the step size. Step size depends on the reference voltage and the number of output bits, and it comes out to be 6 to 5 millivolt. Third one is the conversion time. It's the time ADC takes to convert the analog input to a digital number. Usually conversion time depends on the clock source as well as the method used for data conversion and the manufacturing process as well. And then next one is V reference, that is reference voltage. V reference and resolution of ADC decides the step size, and also V reference should be less than the input voltage, because if we keep V reference greater than the input voltage, then there may be a chances of losing data. So next point is the types of ADC. After characteristics, we'll think obviously about the types of ADC. Then first one is the successive approximation ADC. Next is flash ADC. Third one is digital RAM or dual slope ADC. Successive approximation ADC is popular because of its faster speed. It is much faster than the digital RAM ADC because it uses digital logic inside a ADC to converge on the value closest to the input voltage. Means we are comparing the input voltage with the output. For this, comparator is used. This is the typical diagram of successive approximation ADC circuit, and here we have used comparator, SAR resistor, inbuilt ADC in the SRG resistor. This is a simple flow of how successive approximation ADC works. First, let the V in input voltage be 5 volt and the SAR resistor is initialized to 1 0 0 0 0 0 0, means keeping MSB bit 1 and all other bits are 0, and this digital value is given to the DAC. Then what DAC does is, DAC converts this digital value into an corresponding analog value. Then this analog value is given back to the comparator, and comparator compares the output of DAC with the input voltage. And suppose if the output of DAC is greater than Vs, that is input voltage, DAC output is greater than Vs, then comparator sends signal to SAR to clear the bit. Then we have to clear that bit and switch to the next bit, making that bit 1 and continue the procedure. But suppose if the DAC output is less than the Vn, then left that bit as it is 1 and switch to the next bit and do all this procedure for all the 8 bits. At the end of 8 clock cycle, you will get an 8-bit digital output, and we take that output in SRG register. Finally, we get a binary output. So this is a simple but sweet working of successive approximation ADC. Then next one is the ADC 0808. As we know, ADCs are available in integrated circuit forms. One of them is ADC 0808. This ADC uses the successive approximation method for conversion of analog to digital signal. This is available in 28-pin DIP package. There are 8 analog channels, that is IN0 to IN7. So we can connect 8 analog inputs at a time, and for selection of these channels, they have provided with the address select lines, that is A, B, C. If A, B, C are 0, 0, 0, then IN0 is selected, and if 0, 0, 1, then IN1 is selected, and so on. Then one is the digital output pins D0 to D7. These pins are used to display the output, digital output. Next is the SOC, EOC and OE. These are the control pins of ADC 0808. First is SOC. SOC means start of conversion. When we give a low to high pulse to SOC, then conversion of analog signal starts, and Next one is the EOC, that is end of conversion. And when the conversion is completed, then EOC sends a low to high pulse on pin number 7. Let me repeat this, guys, because SOC, for start of conversion we are giving the low to high pulse, and at the end of conversion the EOC pin senses the low to high pulse. Means if you are want to check whether the conversion is complete, then you have to check the status of EOC pin. The next is the OE, that is output enable. When the conversion is completed, the result is stored in the registers of ADC 0808, and if you want the result on D0 to D7 bits, then you have to give a high to low pulse to OE pin. Then clock. The clock ranges from 1000 kHz. Usually we give a 640 kHz clock. It's also an important parameter because it decides the conversion time of ADC. Next is the Proteus simulation of ADC 0808 interfacing with 8051. Here first is the IN0 channel, IN1 to 7. These are the analog channels, and to IN0 channel we have connected a potentiometer. And for the selection of this channel, we have provision of A, B, C select lines, address select lines. These are connected to P2.0 to P2.2. And the ALE, which I forget to tell, is the address latch enable. This pin is used to latch the address of analog channels from the ADC 0808. And the next is the V reference, which is connected to plus 5 volt, minus V reference to ground. And the output pins are connected to the port 1. And EOC, OE and start pins are connected to the port 2. And for the display of potentiometer value in terms of hex, we have used a LCD. And the data pins of LCD from D0 to D7 are connected to the port 3, and the control pins RS, RW and EN are connected to the port 0. We'll see the program of ADC interfacing with 8051. This is the simplest program. Don't go on the count of files. For just our simplicity, I have made different files. First is the header file, in which I have declared all the variables which I am using in this program. The add A, add B, add C. These are the select lines used for selection of the analog channels. As we have discussed earlier, these are connected to P2.0, 1 and 2. The ALE, SOC, EOC, these are the control signals. These are connected to port 2. And these are the functions void WRCMD unsigned char. Means we have declared a function WRCMD, and the value to this is the unsigned character. Likewise, there is WR data function, DLMS function and LCD init function. We have just here declared all the variables and functions. Declaration file is there. And next is the file in which we have defined all the functions. First one is the void WRCMD unsigned character C. This function is used for sending commands to the LCD display. And if you have seen the tutorial series on LCD interfacing, then you might recognize that we are making RS equal to 0 for sending commands for LCD display. And as usual, as we are writing the data to LCD, then we have to make RW equal to 0. And we have to give a low to high pulse on EN to enable the internal latch of LCD, so that the latch can take the data. And we have given the 0 to EN and then 1 to EN, means we have created the low to high pulse. And C is given to the P3, and to P3 we have connected the LCD, means the command is given to the port 3, means to the LCD. And the next is delay mesh function. This is used to create a simple delay. Next is the void LCD init function. This function is used for initialization of ADC. First we have made all the control signal 0, and then we have given the 0 cross 3F command 3 times for the initialization of LCD, and there is a command 0 cross 38. This command is for selection of the 2 lines of LCD and the 5/7 matrix, and the 0 cross 08 is for display of cursor off command, and the 0 cross 01 is the clear display screen command. And after that we have given a 0 cross 06 command for incrementing the cursor to the next address, and then 0 cross 0E is for display on cursor blinking. Then LCD is initialized, then and we can see first is the display is on and the cursor is blinking at last. And these all function, WRCMD function calls the above function which we have seen before, that is first function, this function. Next one is the putchar. As seen before, we have sent the commands, then for sending the data we have write the putchar function, and as you know, maybe knowing, we have to make rs equal to 1, that is register select equal to 1 for sending data. As usual, the same is done as we have done in WRCMD function. Then the next is the main program. The main program starts here. Here before we have seen the sub files, and now we'll see the main function. In main function, the adc.h file which we have created as a header file, we have to include this in the main file. And the next file is the stdio.h. This is the library file in which all the input output functions are declared. And next is the main function starts here. We have taken unsigned char t is as a variable. Then we have called the LCD init function for initialization of LCD. As we have discussed, means the control goes from here to here for this function. Then this function is executed, then control goes back to the next line, that is WRCMD equal to 0 cross 80, means move the cursor to the first line of LCD. Then is the printf function. Printf function calls the putchar function, means we are writing the data to LCD. Then the ADC output is printed on the ADC first line of ADC. Then there is a add a 0b 0c0, means channel number 0 of ADC is selected. Next is the ALE. Low to high pulse is required to latch in address. For ALE, low to high pulse is required, and for SOC, low to high pulse is required to start the conversion. So what we are giving, then P1 equal to 0 cross FF, means we are making the P1 as input port. Then EOC equal to 1. First we make the EOC equal to 1, because after conversion EOC sends the 0 logic 0. Then then it will be easy for us to check. Then here we have given the SOC equal to 1 and then made SOC equal to 0. Then conversion starts. Then while EOC equal to 1, exactly equals to 1, means there is no conversion up till until that point. The program is here, and when the EOC is 0, then control goes to second line, and EOC equal to 0 means the conversion is completed, and we can take that value from P1 to the T variable, and we have displayed it on the LCD, that is %x is used to display the hex value. So it's all about the program for interfacing ADC 0808 with the 8051. Hope you will understand. And next we will see the simulation of this. Now we'll see the simulation of this. Here is the simulation. So in first line the ADC output is printed as we have discussed in program, and on the next line the output of ADC is displayed in terms of hex. Now I am changing the port value, then there is a corresponding change in the output voltage, as you can see here. Means first these are hex values, guys, and first the analog value is given to the analog channel number 0, and the processing is done in the ADC 0808 IC, and we'll get the digital output on this piece. This output is given to the port 1, and as we have written in our program, we'll take the value on the port 1 and will display the hex of that value on the LCD display. It's all about the interfacing of ADC 0808 with the 8051. Hope you have understood. And next is the, if you have any queries, then contact us at walchan.elisa@gmail.com, and don't forget to like us on www.facebook.com/wcelisa. Thank you.